The directions say to show/prove whether each pair of functions are inverses. Now this is different than the previous ones where I said find the inverse functions. This one says show and prove whether they are inverses. And this had a different set of directions. If you're going to prove that they are inverses, then you have to show that the composition of functions, that the f of g of x will give you an x, and it's a two-pronged test that g of f at x is also equal to x. Now remember, these notations here, this idea says that if I put function g into function f, I want to return the same value that we put in. So if they are inverses, that when I put in an input, g is going to give it an output. Then that output that we're going to have is going to go into f, and that output is better give me back the same input. So that's kind of a lot of mixed words in here, but whatever g does, f must undo. So no matter what we put into g, f has to turn around and bring us back to what we started with, x, for any value. So here's our rule. What we have to do is we have to show that if we put in function g into function f, so that means I'm going to put in negative 3x plus 9 into function f, that it would undo it and bring me right back to x. So I want to see if I can prove that it's equal to x. So this is going into function f, so I'm going to pull out function f, which is a negative 1/3. You have to take it times a negative 3x plus 9, then add 3. Will that give me an x? I'm trying to verify that it'll give me x every time. So we're going to keep going down with this idea. I'm going to distribute the negative 1/3, and negative times negative is positive, and a third of 3 is 1, so I'm just left with 1x. Then I take a negative third times a positive 9, so I'm distributing that. That's a negative, and a third of 9 is 3, plus 3, is it equal to x? And a negative 3 and a positive 3 is 0, so I just have x equals x. So I have shown and proven that the f will undo g. So no matter what g does to your input, f's going to turn right around and undo it and bring you back to what we started with. Now that's the first prong of that test. The second prong is you have to do g of f at x. What we want to verify is that g will undo whatever x does to it. So again, our explanation is no matter what we put into function f, that's going to give us an output. G is going to take that output and bring us right back to the initial input that we had as x. So here's what it forces us to do. We want to put inside of function inside of function g, whatever f is. And f was the function negative 1/3 x plus 3. That is going into function g, and we want to prove that it ends up giving us x, the input that we started with. So now we're going to put this into function g. And g says you have to take a negative 3 times whatever your input is, which is a negative 1/3 plus 3, and then add 9 equals x. Now show means demonstrate. If you use your algebra and you simplify, do you get an x? So negative times negative is positive. A third of 3 is, forgot the x in there, let me add the x. So a negative 3 times a third is a positive 1x, and then a negative 3 times a positive 3 is a negative 9 plus 9. Does that give you an x? Well, the negative 9 plus 9 reduce, so x is equal to x. What this establishes is that g will always undo whatever f does to it. So since they each undo each other, we can declare, therefore, they are inverses. Sorry, got sidetracked. Inverses. Okay, now that's your responsibility to show. Make sure you don't shortcut. It's not, I just say, ta-da, there you go, they both equal x. I should see in incremental stages, just like I'm establishing here. I put it in, I do some algebra, I simplify, I get x, the same thing over here. Do both sides. Yeah, they're going to take a little bit more time, but that is the nature of proving that they're inverse.